Hello and welcome back to Technology Now, a weekly show from Hewlett Packard Enterprise where we take what's happening in the world and explore how it's changing the way organizations are using technology. We're your hosts, Michael Bird
and Aubrey Lovell. And in this episode, we're looking at rethinking the way we look at AI, which sounds like no small task. We'll be examining whether we've been doing it all wrong by using machine learning, and instead whether we should be looking at AI as more of a map. It's something called physics-based AI, and it could save a fortune in training and operating our AI systems, at least in some cases.
Wow, so another big topic this week. So if you are the kind of person who needs to know why what's going on in the world matters to your organization, this podcast absolutely is for you. And if you haven't yet done so, do make sure you subscribe on your podcast app of choice so you don't miss out. Right, Aubrey, let's dive straight in. In last week's episode, we looked at how certain kinds of AI problems need us to rethink the way we build computers, a field known as novel accelerators. This week, we're looking at whether the way we design AI and machine learning needs to change in order to reduce costs and energy usage. And the numbers speak for themselves, because according to the World Economic Forum, the greenhouse gas emissions of certain generative AI providers has risen by nearly 50% in the last 5 years, a rise largely tied to increased energy demands in data centers. The same report found that generative AI uses 33 times more energy to complete a task than specialized software would, and that training some of the latest large language models use the same amount of electricity as, get this, 6,500 US homes would annually. My goodness.
Wow.
And incredibly, the same report concludes that the computational power needed to sustain the AI industry's growth is doubling every 100 days. And if you want to know more about that, the report is linked to in the show notes.
Meanwhile, 1% of global electricity use is already dedicated to running data centers and data transmission networks, according to the International Energy Agency, or IEA. And we've linked to that in the show notes as well. Now, clearly that's not sustainable. So how could changing the way we look at AI to make it less of a repetition exercise and more of a physics problem help? Well, we're joined again this week by Ray Beausoleil. Ray is a physicist, senior fellow, and senior vice president at HPE, and he leads the large-scale integrated photonics lab at Hewlett Packard Labs. So, Ray, the obvious question, what is physics-based generative AI?
It is using what we have learned in physics, particularly statistical mechanics, statistical quantum field theory, to help us build better large language models, to help us build better neural networks. So there is an approach called energy-based models. But the idea is to think more of trying to solve an optimization problem. And this is actually a very important point to make. At the heart of every machine learning problem is an optimization problem, where you are searching across a landscape, and the high parts in the landscape are actually bad solutions to the problem you're looking for, a bad neural network, if you will. And low points in that energy landscape, that feature landscape, are the good solutions. This is actually, now I'm actually onto something. I am creating a model that is true or close to true. The basic idea of an energy-based model, probably the most well-known example of physics-based generative AI, is that it says, okay, well, if we're going to essentially create this landscape and call it an energy landscape, let's treat it like an energy landscape in a real physical problem. The physics-based Gen AI idea decouples training, fine-tuning, and inference from this mathematically complex and numerically expensive approach where you wash information forward and back across a neural network. That's what back propagation is. You say, all right, well, here is where I am now in the evolution of my neural network. How good is it? Well, let's look at where this solution sits on the energy landscape. Well, that's kind of high. Let's change the values of all the weights behind us all the way back to the beginning. So then you carry the problem forward again, figure out where you are now. Then you wash all that information back so that you can try again, and you keep doing this. And this is why it takes so long and why it's so incredibly difficult and why GPUs have become scarce, because the companies that build them just can't make them fast enough. Energy-based models say, let's approach this problem differently. And without getting too technical, one of the ways to think about it is that it operates by always going forward. So it has a different way of improving where it sits on the energy landscape by thinking about it as a physics problem that doesn't require it to send all that data all the way back and then to try again. And so it just treats the problem of finding the minimum of that energy landscape like a physics problem, where you're always going forward, you're never going backward, and you, in principle, can save an enormous amount of computation, which is costly in both time and energy.
So, Ray, does a physics-based large language model need training in, I guess, like a different way to a traditional large language model?
No, it is a completely new architecture, but it absolutely does need training. And in fact, that's one of the key problems. They are hard to train. I'm trying to think of a non-technical way to say this, but I can't. Maybe a smarter person than me could, but I can't. So instead, I'm just going to make the point that it's taking a very general connectivity map between all of the variables that you're trying to solve. It's incredibly difficult to train an energy-based model over that general landscape. And it also has very poor scaling. It becomes really difficult to train and then even to do inference when you've got only discrete variables that can be 1 or 0, for example. Our research, which I'm not prepared to discuss because I don't want to alert our competitors on how we think we're going to be able to do it, but our research is focused on using techniques from statistical field theory to try to solve those two problems. Because the energy-based models, they have some really enormous advantages. And the biggest one for me, the one that makes it the most interesting to me, is interpretability. So in other words, if you use an energy-based model to do inference, to actually answer questions, once you have trained your large language model, you use an energy-based model to help dig out the data and answer questions. That's what a generative AI system is doing. And so when it's generating an AI response, it does so in a way where you can see what it does and why. And that's absolutely not possible with a neural network trained using backpropagation. It's impenetrable, a black box. And so what you buy is a significant reduction in computation. You get interpretability. You get several other advantages that are very technical. But the price you pay is that you have to solve the training and the scalability problem for discrete variables. And that's where the research is focused right now.
So that could be amazing for something like fintech, right? Or other fields where accountability and traceability is really important. Are there any other major advantages to physics-based generative AI?
Yes, it's faster, it's more efficient, it reduces time and power consumption for training by orders of magnitude. There are a lot of technical reasons to do it, but at this point in time, my guess is that a better technical case can be made for joining conventional neural networks and energy-based models so that, for example, it may still be, if you have 100 billion data points instead of 100 trillion, it may still be best to sort through all of that data using a conventional neural network. But then for fine-tuning, figuring out how to ask better questions, better prompts for the generative AI, and for interpretability, for inference, you'd get a better result using an energy-based model to make an energy-based model part of the training process for the LLM. There essentially isn't a technical area where if, and this is a big if you can solve the problems of the difficulty of training and the discrete scaling, then there are essentially every place that generative AI is used now would benefit from incorporating energy-based models into the training and definitely then in fine-tuning and inference.
Awesome. Thank you so much, Ray. That was really fascinating.
Okay, well, right now it's time for Today I Learned, the part of the show where we take a look at something happening in the world we think you should know about. And I think this week it's your turn, Michael.
Yes, it is. Thank you, Aubrey. And I've got potentially great news today for type 1 diabetes sufferers. A suite of novel, specifically engineered insulins are being developed which could revolutionize treatment for the condition. A collaboration between several charities in the UK and 6 global research projects is aiming to develop a series of new insulin types, which will only activate when blood glucose reaches certain levels. The so-called smart insulins being trialled work by sitting in the bloodstream until being activated, and they are only active until glucose levels drop again. This avoids potentially dangerous hypoglycemia or low blood glucose. By being far more accurate with their dosing and release times, it also means that insulin would only need to be injected once a week, with further regular top-up injections rather than constant measurement and micro-injections people with diabetes are used to today. The various different smart insulin projects are in different phases, but it's hoped that by bringing together the projects and offering funding, they will be able to get them into the human trial phase and out to patients in the relatively near future. Wow, that is absolutely brilliant.
That is incredible news.
Big fan of that project.
Absolutely. It can change so many lives, right? So What a great story. Thanks for that, Michael. All right, well, now it's time to return to our guest, Ray Beausoleil, to talk about physics-based AI. So, Ray, we talked a little before the break about training these new AI systems compared to traditional machine learning. Are they essentially hardware compatible, though? Could I, for example, load up a physics-based generative AI model on a traditional GPU-based machine learning system?
In principle, it can run off the same platforms, but once again, the energy-based models can benefit from a different computer architecture so they can run faster and more efficiently. And components of physics-based Gen AI can benefit tremendously by, for example, technologies that are directly related to the energy landscape that the Gen AI system, especially the energy-based model approach, is mimicking. And so, yes, your answer is that they are, think of novel accelerators and physics-based Gen AI as being on parallel paths right now, and large language models. These are all going to come together within about 10 years, and it's going to change everything.
I guess a final question from us. So why should our listeners be paying attention to the field of physics-based generative AI?
The most important reason to keep track of whether or not those two main limitations, those two challenges can be met, is that large language models, conventional Gen AI, will become more useful for many more applications and may in fact become useful to most of us who work in medium to large companies. Am I bold enough to say it will change the way small businesses operate? Probably not. People I hired who are in fact subject matter experts believe that. Probably yes. The reason is that all of the hype and all of the noise being made about whether large language models are in fact intelligent, which I do not believe, would become different if we could figure out a way to add planning and reasoning to what we currently call AI. And I think physics-based models are a likely way, if they can work, are a likely way to make that possible. And that would suddenly change how useful they are. Because right now, if you ask a large language model to plan your vacation, they don't know how to do that. What you really want is not something that just makes all the decisions. What you want is something that gives you a lot of options. And even that, the more complicated you are, and the more complicated your vacation goals are, and the amount of time you have will change the quality of the answer that you require. I think that the thing to remember about AI as it exists is, number one, it's really just machine learning at this point. There isn't anything I about it, although it's very A. Our goal is augmented intelligence, but that cannot happen until generative AI incorporates planning and reasoning. So pay attention to physics-based generative AI, particularly energy-based models, because that may be a way of getting to the point where planning and reasoning coincide, work together with these large language models to do something remarkable.
Thanks so much, Ray. It's been great to have you on the show. And you can find more on the topics discussed in today's episode in the show notes.
Right. Well, we are getting towards the end of the show, which means it is time, of course, for This Week in History, a look at monumental events in the world of business and technology, which has changed our lives. Aubrey, can you please remind me of last week's clue?
Well, the clue last week, Michael, was it's 1831, and this bright spark really got us moving. So we went way, way back, and it was obviously the discovery of electromagnetic induction by English scientist Michael Faraday.
Oh.
Now this,
That wasn't what I was thinking at all. I was thinking of the internal combustion engine.
Yes.
Yes, I've got that very wrong. Right. Sorry.
Well, the discovery that by changing an electric field, you could create motion within it was obviously revolutionary at the time. In Faraday's first experiment, he wrapped two wires around the outside of an iron ring and applied a charge to them, generating what he saw as a, quote, wave of electricity. Now, within 2 months, he found he could create the same effect by sliding a magnet through a coil of wires and a steady current by rotating a copper disc near the magnet. Sounds complicated. However, Faraday's findings were almost universally rejected by the scientific community because he didn't present them as mathematical findings, just as physical experiments. Nevertheless, enough people picked up on the idea and carried it forward that Faraday's findings brought about an electrical revolution, spawning our modern understanding of electricity generation and electric motors. So, pretty big find.
Thank you, Aubrey. Now, the clue for next week is it's 1985, and this satellite's story is one long tail. Know what it is, Aubrey? Any idea?
Actually, I don't.
No.
I do not.
I also do not, but we will find out next week, won't we?
We will.
Now, that brings us to the end of Technology Now for this week, and a huge thank you to our guest, Ray Beausoleil, Senior Fellow and Senior Vice President at HPE, and leader of the large-scale integrated photonics lab at Hewlett Packard Labs. And to you, of course, thank you so much for joining us.
Technology Now is hosted by Michael Bird and myself, Aubrey Lovell, and this episode was produced by Sam Data Paulin with production support from Harry Morton, Zoe Anderson, Alicia Kempson-Taylor, Allison Paisley, Alyssa Mitri, and Camilla Patel. Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, Katie Guarino, and our social media designers are Alejandra Garcia, Carlos Alberto Suarez, and Ambar Maldonado.
Technology Now is a Low Street production for Hewlett Packard Enterprise, and we'll see you at the same time, the same place next week.